Two very important inequalities that I will use in this video are the following. A minus b all squared is greater than or equal to 0 for all real numbers a and b, and a plus b squared is greater than or equal to 0 for all real numbers a and b. Now the reason that's true is because if you square anything, it's going to be positive. So these are well worth remembering. Well, they're easy enough to remember because you're just squaring something, it's positive, but the consequences of them are quite interesting. Like if we take this first inequality here and expand it out, square the first term, multiply first by second and double, then square the second term, we end up proving this thing here, which is not so obvious. So this is true for any real numbers a and b. And we can use this result to answer the first part of this question. What we do is we simply add ab onto both sides. So if we add ab here, we get a squared minus ab plus b squared. And then we add ab onto the right hand side. And that's what we had to prove in part 1. Let a and b be non-zero real numbers such that a plus b is greater than or equal to 0. Show that a over b squared plus b over a squared is greater than or equal to 1 over a plus 1 over b. So we're given that a plus b is greater than or equal to 0, and we're also given that a is non-zero and b is non-zero. Now, we start by assuming this is true, and we deduce some consequences, and hopefully we will end up with something that we know to be true. And then we can reverse the steps. So that's the idea. So I'll start with this. And what I will do is get it into a straight line. Now to get this thing into a straight line, what you do is multiply all of it by a squared b squared. That way you will be able to cancel out all the denominators. And by the way, multiplying by a squared b squared won't affect the direction of this inequality, because a squared b squared is clearly positive. Because a squared b squared is something squared, it's actually ab squared, and anything squared is positive. Also, it's not equal to 0. You won't find it equal to 0 because a is not 0 and b is not 0. Another reason that a and b can't be 0, well, a reason that a and b can't be 0 is because then we would have division by 0, and that's not defined, of course. So we multiply a squared b squared by a over b squared. Well, that's going to give us a cubed b squared over b squared, and the b squareds cancel to give us a cubed. Then we have a squared b squared times b. That's going to give us a squared b cubed over a squared. A squareds cancel and we get b cubed. Over here, if we multiply a squared b squared by 1 over a, one of the a's will cancel, so we're left with ab squared. A squared b squared over b leaves us with a squared b, because one of the b underneath cancels with one of the b's and b squared. Now the next thing I can do is factorize the right hand side. I can take ab out of the right hand side. So if I take ab out of this term, I have b, and I have to have b to get back ab squared, and I have to have an a here because ab times a is a squared b. The next thing I will do is factorize out the left hand side. The left hand side is referred to as a sum of two cubes. The sum of two cubes can be factorized into a plus b times a squared minus ab plus b squared. So this is worth knowing. Simply multiply it out if you want to check it. Now you can see that a plus b appears on both sides. So you might think we just divide both sides by a plus b, but we have to be a little bit careful. We have to make sure that a plus b is not 0. We're given in the question that a plus b is greater than or equal to 0, so it could equal 0. So we need to consider two cases. The first case is where a plus b is not 0. Well, not 0 in this case would mean that it's greater than 0, because we're given that it's greater than 0. So I could just put greater than 0 here, which is not 0, of course. Okay, so it's either greater than 0 or equal to 0. Now, if it's greater than 0, then we can just cancel it from both sides. If it's equal to 0, we can't divide both sides by 0. So what are we left with? Well, we're left with a squared minus ab plus b squared greater than or equal to ab. Now, is this true? Well, it is. We proved it in part 1. As a matter of fact, this thing is true for all real numbers a and b. So it doesn't matter about whether A and B are greater than 0 or not. So this is true from part 1. So now we have to look at the second case where we can't divide both sides by A plus B. That is a situation where A plus B equals 0. So A plus B is either greater than 0 or equal to 0. But if A plus B is equal to 0, it means that A must equal minus B. So we want to prove this inequality, but we use this here, use this fact for this case. Replace A with minus B, so we have minus B over B squared. When we replace this A with minus B, we have minus B times minus B is plus B squared. On the right hand side we replace A with minus B, so this fraction becomes minus 1 over B. And then we have plus 1 over B. Now is this true? Well, it is, because these cancel out to give 0, and minus 1 over b plus 1 over b is also 0. And it is true that 0 is greater than or equal to 0. So we actually get equality when a plus b is equal to 0. So we've taken care of both cases, where a plus b is greater than 0 and a plus b is equal to 0. So what we could do then is just reverse our steps for both cases, and we've proven this inequality. Show that if a and b are non-zero real numbers, then the value of a over b plus b over a can never lie between minus 2 and plus 2. Let's just look at an example. Here I've chosen a to be 1 and b to be 2. Then a over b plus b over a is going to be 1 over 2 plus 2 over 1, which is 2.5. So you can see that for these values at least, then a over b plus b over a does not lie between minus 2 and plus 2. We get a value that's greater than 2 actually. Here is another example. Suppose a equals minus 1 and b equals plus 1. If we calculate a over b, we get minus 1 over plus 1, which is minus 1. If we calculate b over a, we get plus 1 over minus 1, which is minus 1. And if we add these numbers together, we get minus 2. Now, minus 2 is not a number that lies between minus 2 and plus 2. So what we mean by lying between minus 2 and plus 2 is that this expression here cannot equal minus 2 or plus 2. It must be some number between minus 2 and plus 2, but cannot equal either of these numbers. That's what's meant by lie between in this case. Another thing to consider is that neither a nor b can equal 0, because if a or one of a or b equal to 0, then we would have division by 0 in this, and we can't have division by 0. So a and b are any non-zero real numbers. So those were a few examples. Of course, those few examples suggest that this expression does not lie between minus 2 and plus 2, but those few examples do not constitute a proof. We want to prove this is true for all values. So what I will do here is suppose that a over b plus b over a does lie between minus 2 and plus 2. In other words, minus 2 is less than a over b plus b over a, which in turn is less than 2. And what I will do with this is deduce some consequences until we get to something that is clearly false. And that means that this original statement must also be false. So we'll just assume that this is true. And what I will do next is multiply everything by AB to get rid of these denominators. Now that's where we have to consider two cases. When we multiply both sides by AB, well, the direction of our inequality signs will be affected if AB is negative. So we have to consider two cases. Case 1 is where the product AB is positive. That will happen when both A and B are positive, or when both A and B are negative. So that's one case. And the second case is where A times B is negative. That will happen when A is positive and B is negative, or A is negative and B is positive. Now these are the only two cases to consider. We don't have a third situation. We don't have a case where AB is equal to 0. AB cannot equal 0 because we're given that both A and B are non-zero real numbers. The only way to get 0 is if one of these numbers is 0 and neither of them is 0. So we don't have that third case. So there's only two cases to consider. So when we're simplifying this inequality, we have to take into consideration the sign of this product AB. If AB is positive, then our inequality signs remain as less than signs. But if AB is negative, then our inequality signs will change direction. If we multiply an inequality by negative quantity, then these less than symbols become greater than symbols. So the first thing I will do is consider the case where AB is positive. So we multiply all of this inequality by AB, where AB is a positive quantity. If we multiply the left-hand side by AB, we get minus 2AB. If we multiply this expression here by AB, what will happen is we will cancel B in this denominator, and we will end up with A times A, or A squared. And when I multiply AB by this fraction here, A's will cancel and we get B times B, which is B squared. Then I multiply the right hand side by AB, so you get 2AB. Now it's not so clear whether this is true or not, but let's try to work 0 into this. So we're going to try and use the fact that A plus B squared is greater than or equal to 0. Or we're going to try to use the fact that A minus B all squared is greater than or equal to 0. Something squared is positive. So we try to work 0 into this inequality. And one way to do that would be to add 2AB to everything here. So if we add 2AB to this here, we get 0. If we add 2AB here, we get A squared plus 2AB plus B squared. And adding 2AB onto this part gives us 4AB. So that's just adding 2AB to all parts of our inequality. And that's allowable, of course. We can add the same quantity to any part of an inequality and we do not change that inequality. We can also subtract something from all parts. Now, then we might look at this and see if it's a perfect square. That means we want to see if both its factors are the same. And they are. We can actually write this as A plus B squared. So that tells us that the first part of this inequality is indeed true. A plus B all squared is indeed strictly greater than 0 if we read backwards. A plus B squared cannot equal 0 because we have started out by assuming that A times B is positive. If A times B is positive, it means that A and B cannot have opposite sign. You know, if we want A plus B to equal 0, then A and B would have to have opposite sign. For example, if A was plus 2 and B was minus 2, then we would have 0 here. We'd have 0 squared is greater than 0, which is false, of course. But that can't happen, because if A times B is positive, then A and B have to have the same sign. So this can never be 0. So this part is true, provided that AB is greater than 0, and that's what we're assuming. Now, let's look at this part of the inequality. So we have the case that A plus B squared is indeed greater than 0, but is it less than 4AB? So now let's look at this part here. Okay, it's not enough that A plus B squared is greater than 0. It must be less than 4AB. It must lie between 0 and 4AB for this inequality to be true. Actually, the easiest way to look at this is to get 0 on one side. So if you subtract 4AB from both sides, we will have 0 on the right hand side. So we're subtracting 4AB from plus 4AB to get 0. So we have to subtract 4AB from this thing. Now I'll expand this thing out again. We get A squared plus 2AB plus B squared, subtract 4AB. And if we simplify this here, we get A squared minus 2AB plus B squared less than 0. But look, we can factorize this here. This is a perfect square. The left hand side can be written as A minus B squared. So here is our important inequality coming in. Now, is this true? Clearly it isn't, it's false. Because if we square anything, we always get something that's either greater than 0 or equal to 0. It can never be less than 0. A minus B squared can never be negative. It's either equal to 0 or greater than 0. So that tells us that this inequality here is false, that A plus B squared does not lie between 0 and 4AB. As a matter of fact, A plus B squared is greater than 4AB. So then we can reverse all of our steps and conclude that our original inequality is false when AB is greater than 0. So that's the situation where the product AB is greater than 0. And then we consider the second case. That's where the product AB is less than 0, which can happen, of course. A could be positive, B could be negative, or vice versa. So what we do now is we multiply our inequality by AB, and we're assuming that AB is negative. So we multiply AB by this part here to get minus 2AB. When we multiply AB by the expression in the middle, we'll end up with A squared plus B squared as before. AB times A over B is A squared. AB times B over A is B squared. When we multiply 2 by AB, we get 2AB. But the direction of our inequalities reverse, because we're multiplying this inequality by a negative quantity. Just to remind you of why it reverses, let's take a very simple example. We know that 2 is obviously less than 3. Well, if we multiply both sides by minus 1, we get minus 2 on the left hand side, we get minus 3 on the right hand side, and you can see that minus 2 is actually greater than minus 3. So you must reverse the inequality when you multiply an inequality by a negative value. Now we do something similar to what we did before, which is to try to bring 0 into this. So what I will do is add 2ab onto all three parts of this inequality. If I add 2ab onto minus 2ab, I get 0. And if I add it in here, I get a squared plus 2ab plus b squared. If I add it here, I get 4ab. This middle expression here is actually a perfect square. It's a plus b squared. And that is indeed greater than 0. Or, sorry, it's not actually. We can see here it's less than 0. So this is false. This thing here is actually greater than 0 because it's a square. So it should be on the other side of 0 if you like. You know, this inequality is not written down with the usual sense where you have the smallest part first. If I write it down in the usual sense, you have 4ab less than a squared plus 2ab plus b squared less than 0. And this part here is false. So this expression here is on the other side of 0. It doesn't lie between 4ab and 0. So that proves that our original inequality is false for case 2. And these are the only two cases. So that means that a over b plus b over a does not lie between minus 2 and plus 2. So by starting with this inequality here, we end up getting a contradiction. And we got a contradiction for both situations, when ab is positive or negative. So that means that this is false, our original supposition, and it means then that a over b plus b over a is either less than or equal to minus 2, or it's greater than or equal to plus 2. Now, this expression here could actually equal minus 2, and I showed you an example of that. If we let a equal 1 and b equal minus 1. And this expression could actually equal 2 if we let a equal, say, 3 and b equal 3. Then we have 3 divided by 3, which is 1, plus another 1, which is 2. So we get equality when we get this expression equal to plus 2 when both a and b are the same. And we get equality here with minus 2 when a and b have opposite signs.